In today's lecture, we've got two different concepts. One is inverse velocity kinematics, and that is, how do we tell the joints of our robots how to move in order to achieve the velocity we want at our end-effector? And the other one is manipulability, and they're both tightly related. It helps if we look at this animation. So here I've got a complicated 7 degree of freedom robot. Here I can move some of these prismatic joints, so we can sort of see what's going on here. I'll move this prismatic joint as well and pull that out there. Now you can sort of see what this robot is. It's got 7 degrees of freedom, which is more than we normally need. And the question is, well, now is everything accessible by this robot? Can we go in any direction? And so to show that, I'm going to show the manipulability ellipse. And what you can see here is this ellipse is three-dimensional, and so it can achieve any desired velocity within this neighborhood of this position. However, one thing that it can't do is that it cannot achieve arbitrary orientation rotations. And so this is a two-dimensional set. It's in a singularity position. If we move one of these joints out, well, this joint isn't going to pull us out because it's at the last joint. But if I rotate this one off axis, then suddenly we can get out of that region. And so this is one of the tricks of this manipulability ellipse. It shows when we are in a singular position. And I've split this into the velocity and the angular velocity. So that's one concept we're going to look at today. So here's another concept we'll look today. This is a 7 joint robot. It's all a planar robot. And you can see it's currently in a singular position. It's singular for both angular velocity, but also the velocity. The angular velocity isn't interesting in this case because all the axes are going to be aligned with here. Let me get it out of this position so you can see something a little bit more interesting. As soon as we pull this out, now we've got a robot that is a little bit easier to see its configuration ellipse. Let's pull this out here. You see, as I've been moving around, this ellipse of velocities it can move in has become more and more circular. This is just showing how easy it is to move in different directions. It was in a singular position when it was all lined up, and now it's been pulled out of that. In fact, that singular position is a little bit hard to find because you have to have everybody completely lined up. So they can either be all straight out in one direction, or they can be folded up on each other. But those are the only singular positions for this because it is highly redundant. But it can get into those singularities. And one question you might have with this robot is, how should we steer this most efficiently? So this says that I can move in the red direction or the blue direction or any of these other directions. And there's lots of ways with 7 different joints that we could make that movement. As an engineer, we'd like to do that most efficiently. So we'll see how to do that today. Now this slide has just about all the math that we're going to need today as we talk about inverse velocity kinematics. We're going to learn about something which is called the pseudo-inverse, because we want to invert this Jacobian, but sometimes this Jacobian is not an invertible square matrix. And so we need a different trick to do that. And so since we can work on the right side because we're controlling our joint velocity, we need something that we can insert on the right side. And so that is the right pseudo-inverse. In order to really understand what's going on with this, we're also going to talk about the singular value decomposition, and that'll cover that topic. In manipulability, we are going to be looking at what is this ellipsoid, how do we build that? And to do that, again, we're going to use a singular value decomposition, but we're going to split it up and show how we can express this ellipsoid as a function of our Jacobian and the desired velocities. So here's today's handout. And let's just do a little bit of review. We know that when we talk about our robots, we talk about their configuration with a Q. And when we do forward kinematics, what we're doing is we're moving from our robot configurations into where is that end-effector, and that is in special Euclidean space of dimension 3. So remember that special Euclidean, it's going to have a rotation matrix. It'll have a 0, 0, 0. Then over here it'll have the offset and a 1. And we get our 4x4 matrix, which is an element of SE3. In order to do this, we have to generate our different homogeneous transforms, which we called our A and then our T matrices, where we have one A matrix for each joint, and then those can build up to be our total transformation. by multiplying them together. Now when we do inverse kinematics, we're doing the opposite. We're going from SE3 back into our joint configurations. We found that that was hard because there can be multiple solutions. Sometimes there's a bunch of different values of Q that will give the same end effector position. But also there can be these times when there's no solutions. An easy example of when it's out of the workspace. There's no way that it can, if it's beyond the reach of the robot, there's no solution to that. Now, our solution to this was twofold. First, to find our velocities, we would just project into a lower dimensional subspace. And once we were there, then we would just solve a geometric problem. So we'd try to figure out what are the angles in order to solve this. To do our orientation, we would use kinematics decoupling. And if you remember, that only worked because we always said we're going to put a spherical wrist at the end. And so that simplified our problem. We could find the wrist center, remember, wrist center, and then you'd solve for position with the first three links, and then you'd solve for the Euler angles for the spherical wrist. So that solved our inverse kinematics. Now when we want to do forward velocity kinematics, what we're doing is we're going from q dot, how fast we move each of our joints, into psi. Where the psi, we take our q dot and we multiply it by our Jacobian to get our psi. And our psi could be divided into our linear velocity and our angular velocity. To do this, we needed our skew symmetric matrices to represent our rotation, and then we could break up our Jacobian in the top rows, which are for velocity, jv times q dot, and we could have our j omega times q dot. And we had a little recipe for how we build our Jacobian, and hopefully everybody made a crib sheet to remember that, but there were 4 cases. So the forward velocity kinematics were also not too challenging after you build that crib sheet. So let's do a little example. Let's say that we've got a single revolute joint robot. I've got a picture of this robot here. It can rotate with our theta 1, and its speed is theta 1 dot. And so our x position is just going to be the length of this. Let's say that this one is r1. So x is just going to be r1 times the cosine of theta 1. And then our y is going to be just r1 times the sine of theta 1. And then my theta 1, if I wanted to solve directly from that, well, I would just take my x and my y positions and use my a tan 2. I put my x and my y. And again, the order of those depends on what programming language you're using for your 2-argument arctangent function. Now, if we want to know how is my x position changing, so that would be x dot, then we just take our derivative of this. So the derivative is going to be negative r1 sine theta 1, and my y dot, my speed in my y direction, is going to be r1 cosine of theta 1. Now my speed in my z direction, I've got no component that can move me out of the plane. So that's always going to be 0. And then similarly, I have no way to roll, no way to pitch. The only thing that I can do is yaw. And that is going to be proportional to how fast I'm rotating theta 1. Now we can invert this to try to solve for what theta 1 is. If you had your yaw measurement, you could directly solve for what theta 1 is. But we can also solve if we just have our x velocity. So you just take your x dot and you divide it by negative r1 sine theta 1. And then you'd get your answer. But you can only do that if and only if, that's what the IFF means, if and only if you're getting the same solution for both of those. So x dot over negative r1 sine theta 1 is equal to y dot r1 cosine of theta 1. And there's a couple times when this is not invertible. When this denominator is 0, then we can't solve for this. Let's draw the possible xy velocities that we can do with this robot. And so in this position, the only velocities that it can do are in this direction. So what you could do is you can then split this into our x and our y. So our y components, they could be And then our x components are this direction. That is the only velocity that I can choose. Something along this green arrow. I can scale it up or down, but that's the only instantaneous velocity that I could do. One thing that we could do is then we could try to draw this in 3 dimensions, where we could put theta along this axis, and we could put our x and our y here. And if you drew the different achievable velocities that we can do, each one is going to be a one-dimensional set, but as we build them, then you could get something that looks kind of like a DNA double helix. So I'm going to go ahead and I'm going to show you that. So a valid question that you can ask is, when can we find our solutions to the psi equals j, the Jacobian times q dot? Well, we can only do that if the rank of this Jacobian at configuration q is equal to the rank of an augmented matrix, where we take the Jacobian and then we augment it and we put for the psi. And so if the rank of this is equivalent to the rank of the Jacobian, so that means that psi is in the range space of the Jacobian, then you can find solutions to that. So you can see in this example, in this 1D example, the motion that can achieve is always in a one-dimensional set. So if that psi isn't along this green arrow, then you're never going to be able to achieve that. That's the only velocities we can do. Every other velocity isn't in the range space of our Jacobian for the current configuration. So what happens if you had a robot that has lots of degrees of freedom? Well, this is kind of hard to draw, so let's start with a planar case, where we've got a 3 rotational link planar robot. We've got R1 equals 2, R2 equals 1, and R3 equals 1. And I've taken the liberty to write the Jacobian in for you already. And so now all we have to do is input what this same Jacobian with our joint links. So let's put that in. You do S1. First entry, my next entry is 2S1 plus C12 plus C123. Then everything else here is 0, 0, 0, 1. My next entry is we drop out the first item here and just minus S12 minus S123. We've got cosine 1 plus 2 plus the cosine of all 3 angles. Then 0, 0, 0, 1. My final one just has the 1 entry into it. So it's got negative sine of the summation of 1, 2, and 3, and the cosine, the summation of 1, 2, and 3, 0, 0, 0, 1. And so this is my Jacobian. And so only if my velocity fits in this range space am I going to be able to do that. And so where do we lose degrees of freedom? Well, that is a question that says, where are the singularity? Whenever theta I is equal to ki times pi, for I is greater than 1. We don't care about the first degree of freedom, but everybody else, if they are lined up, they're either lined up, so I can draw that. So if my first joint is here, and then if my next joint, if that's lined up here, if this is pi, and this joint is here, you could also have something like here, here, and then if this one doubled back up, and then it would also be in its singular position. We have to evaluate our Jacobian at a certain value here. So if I put 0, pi over 4, and pi over 2, and I plug that into my equation, so my 2 sine of 0 is going to give it a 0, but my 1 plus 2 is just going to equal pi over 4, and 1 plus 2 plus 3 is equal to 3 pi over 4. And so we can input these in. Sine of pi over 2 is going to be so that gives us enough to solve for this. We've got negative root 2, negative root 2, and negative 1 over root of 2. Then we get some cancellations between the second and third cosine terms, so we only have our 2, and then we've got a 0 here for full cancellation, and negative 1 over root 2. So let's go ahead and let's draw what this robot looks like. So here is my first joint. It's coming right out 0 degrees here. This is length 2. Then I've got my next joint over here coming out of it. So we'll come up pi over 4. I've got my joint of length 1 here. Then my next joint here is going to be at pi over 2. So it makes a right angle there. And so its handle is right there. And so if you think about it, what are the instantaneous velocities that I can make? If I rotate my first degree of freedom, then that's going to make this move in an arc. So instantaneously, I can move it in this direction. If I take my next degree of freedom here, and if I rotate it around here, that's going to instantaneously rotate it in this direction. And then my third degree of freedom, by rotating around here, I can make it instantaneously move back and forth in this direction. And so, since those don't all overlap, I do have control in 2 degrees of freedom there. So here we've got a question. How can we get the end-effector to move at 1 over root 2 and 1 over root 2 in x and y? The question is, what should q dot be to do that? So if you look at it, an easy way to get this, because we've got 1 over root 2 and 1 over root 2 in the last one. And remember, what we're doing is that psi is equal to jv times, well, at configuration q, times q dot. So all we'd have to do this is put a -1 in the last one, and then we could put a 0 in the others two, and we would get that. If we take this and we take the norm of that, well, the norm of 0 squared plus 0 squared plus -1 squared, take the root of that, and we get that the norm is 1. Now, a better way to do this is to compute what is called the pseudo-inverse. Since we can't directly inverse this Jacobian because it's a 3 by 2, what we could do instead is we could say that theta dot is equal to JV transpose times JV times JV transpose, this quantity inverted, times psi. So here's that equation that we just walked through, written out here. And then I've made a little function that just evaluates what is this Jacobian at 0, pi over 4, pi over 2. Here it is in this matrix form. That's just what we had before. And then what I'd like to do is figure out, how do I invert this? And so I take the transpose of this JV times the inverse of the quantity of JV times the transpose of JV times the psi that I want to achieve. And I get this as my output. If I take the norm of that, then I get it's just 0.6785. And then just to prove that this is true, I'm going to take that Jacobian, multiply it by my joint velocities, and I get as output the desired velocities that I wanted to get. So that is giving my answer. This transpose of the matrix times the inverse of the matrix times its transpose is so important that it's built into a bunch of languages. In this case, it's called the pseudo-inverse. So if I just call the function pseudo-inverse of my Jacobian multiplied by the psi that I want, and I get exactly that same answer. So that's how I got that. And so we get a norm here that's 0.67 as opposed to my old norm of being 1. And so how do we get that? Again, this is called the right pseudo-inverse of J. If your Jacobian is an m by n, and if m is less than n, and if the rank of this Jacobian is equal to m, then this J transpose exists. So often, for our robots, our m is going to be 6, and then if that is less than the degrees of freedom of our robot, then we want to ensure that this Jacobian has at least rank of m. And so these Jacobians then, we've got n degrees of freedom in our Q, so we put n right there, and then our Jacobian over here is going to be n by m, because we want to get something that is m tall and 1 over on this side. this n is greater than m, we can get a Jacobian if this matrix has at least rank 6. Because then we're taking this Jacobian, and we're taking Jacobian times its transpose. So just another way to look at that, we've got our Jacobian, right? And it has, m equals 6 by n degrees of freedom. We multiply that by our Jacobian transpose. So that's going to have m equals 6 by n degrees of freedom. Then we get our J transpose is just going to be m by m. So if the rank of my Jacobian was m, then this is going to be a full rank square matrix. And then since it's full rank, then we can take the inverse. And we call this the right pseudo-inverse because we're going to put this quantity where we say that J plus is equal to J transpose times J transpose inverse. We're going to put that on the right side of the J. And so J times J transpose, that's going to give us our identity matrix. Again, this J plus is J transpose J transpose, this quantity inverted. And then Q dot, if we want a Q dot that solves our psi value, well, we can have this J pseudo-inverse times my psi. Then we can also have I minus J right times J itself times B, where B is any vector in Rn. Because if we move inside this vector, where we put this B value in there, this motion here is going to be in the null space. So we get no movement. So the null space is all the vectors that are in I minus J pseudo-inverse J. However, if we want to minimize our joint velocity, so we have that minimum norm, then we'll just say that B is equal to 0. And this is a bold-faced 0. But anything else in there, this gives us our motion. So when you have the end-effector holding still but other joints moving, we're moving in the null space of J. That is given by this pseudo-inverse. So again, when the Jacobian is in m by n, if m is less than n and the rank of J is equal to the m, then we can always find this inverse. This J is going to be in our m by n, m, and it's going to have rank m. And you can show that this is the identity matrix because we're taking J times its J transpose over here. We can split this components up here, and we've got J times J pseudo-inverse. That's our definition of our pseudo-inverse. It is going to give us our identity matrix. Another way that we can look at this is we can take our Jacobian and we can split it with a singular value decomposition. Single value decomposition always gives us 3 matrices: a U matrix, a sigma matrix, and a V matrix, where the U and the V's are rotation matrices, so they're orthogonal matrices. And this sigma is what's called our singular value matrix because it's got all of our singular values. So sigma 1, sigma 2, all the way down to sigma m. It's got zeros everywhere else in this matrix. And then since this is going to be n by m, then it's got n minus m rows of zeros. So we've just got a bunch of zeros in this last column. And these singular values are arranged in such a way that they decrease in value. Sigma 1, sigma 2 is greater than or equal to sigma 3, greater than or equal to sigma m, and then this is greater than or equal to 0. So our Jacobian, it has our singular value of U sigma V transpose. Our pseudo-inverse is a very similar form. It's going to have a V first, that same V. It'll have a slightly different sigma plus here, and then it'll have my U transpose. And that sigma plus value that we have is just going to be the inverse of all of these singular values. So the reciprocal of them. And then again, it has enough zeros over here to make it have n columns. Then we take the transpose of that. And then if you take the singular value decomposition and we multiply it by itself, so j times j plus, we are going to get the identity. So let's just watch how that goes. I put a u sigma v transpose, and then I'm going to multiply that by v sigma plus u transpose. So one of the properties we have is that these are orthogonal matrices. So the v's are rotation matrices. So v transpose times the v, that's going to give our identity matrix. So then we have u sigma transpose u transpose. But since the sigma pseudo-inverse is going to be just the inverse of all my singular values, then I have u times the identity matrix again, times u transpose. And since these are rotation matrices, then I also get the identity. So then we get what we wanted to have here. And so the reason it's a cool trick is because these singular value matrices are easier to work with. They've got this nice diagonal form. So here's a picture showing what the Jacobian does. Remember, the Jacobian takes our joint inputs and then it scales them and makes them into our velocities of our end-effector. And so we can split that up into a V matrix, which rotates this, a scaling matrix, sigma, which stretches it, and then a final rotation matrix that rotates it into our frame for our end-effector velocities. So here's an animation of what happens. So we've got some Jacobian, which scales and rotates this. That can be decomposed into three different matrices. So the first matrix is a rotation matrix. This is our V transpose. Then we've got a scaling matrix, which just stretches it in different directions according to the sigma values. Where we got sigma 1 and sigma 2 here. Then finally a U matrix, which rotates it into its final form. And so this total transformation is U times sigma times V transpose. So now it's time to talk about the manipulability. And this is just a metric that we can talk about how easy it is for the robot to move around at a certain configuration, to arbitrarily to move. And so the game that we play with it is we say that our set of inputs are going to have unit norm. So that means that my q dot, the norm of that, is going to be less than or equal to 1. That means the unit norm. Just to remind us what that looks like, that means I could take all of my components here, q1, I could square that, plus q2 dot, and I could square that. I could go all the way to my qn, because I've got n degrees of freedom. And I square all those, it's going to be less than or equal to 1. I don't have to take the square root because I'm picking this unit norm. So the minimum norm solution then for this, what is, if I want to achieve some psi, what I do is I multiply it by the pseudo-inverse, and that gives me my minimum norm solution. So somebody says, well, I want to move at some psi value, 4, 5, 6. Well, I multiply that by my J transpose, and it gives me my minimum norm solution for Q dot. And so another way that I can rewrite this norm is instead of saying Q dot, take its 2 norm, I can just take Q dot transpose times Q dot. And because of that, then I can insert this other side in here. So that's going to be my pseudo-inverse times my psi transpose times my pseudo-inverse times my psi. And I can split that out a little bit because I can put my transpose through there. And so I've got psi transpose times j pseudo-inverse transpose times my j pseudo-inverse times my psi. And just remember that my pseudo-inverse is equal to j transpose times my j transpose inverse. So we can leave that part as an exercise to the reader, but we get psi transpose times the quantity of j transpose inverse times psi. And this one always has to be less than or equal to 1. That's our solution. And so then my q dot squared, again, this is my psi transpose times j J transpose inverse times psi. If I put my singular value decomposition there in for my J, then my V's are going to cancel, and I will get U transpose psi, this quantity transpose, times my sigma matrix to -2 times my U transpose sigma. You can work that out, but this singular values that we have in the middle, it's going to be sigma 1 to the -2, sigma 2 to the -2, all the way down to sigma m to the -2. And so now if we make a little substitution, just call these values W and W, and we have the formation W transpose times a sigma m -2 inverse times W. That is equal to a summation now, Wi squared over sigma I squared. And again, this entire summation has to be less than or equal to 1. So what we have here is an equation for an axial-aligned ellipse in a different coordinate system. So this coordinate system is obtained by rotating by U transpose, and the axes of my ellipsoid are going to be sigma I times my UI value. The volume of this entire ellipsoid is going to be some k times sigma 1 times sigma 2 all the way out to sigma m. This k that we have is just a constant that depends on the dimension of the ellipsoid. So if m is 2, then we've got a planar case, and so my volume is just going to be pi times my axes. So if we had a circle, then it would be pi r squared. If they're distorted a little bit, we have a different value. If I'm in 3 dimensions, then my k is going to be 4 over 3 pi, and I've got the traditional volume. Then it just scales upwards past that. But the important thing is all of these axes that are multiplied together. We call mu the manipulability measure. And we call that is equal to the volume of this ellipsoid. So this volume of the ellipsoid is equal to 0 only if the rank of J is less than m. So we're in a singular value. The other useful thing that you can do with this is if you've got an error in the measured velocity delta sigma, I can make a ratio there where I've got my maximum error in epsilon, and I can divide my maximum error in my q dot. And this value is always going to be between my minimum and my maximum singular values. So it's going to be between sigma 1 to inverse and sigma m inverse. So if I am in the part of my manipulability ellipse where it's very much like an n-dimensional sphere, then I'm going to be able to bound my velocity well. So this is good. If I get into ellipse that'll look very cigar-shaped, then that's bad. This measure isn't going to do much anyway. But this is this manipulability measure that tells you what's the best place to put my workspace or my object that I'm working on. Where do I have the most ability to move in arbitrary directions? So here's that 3-link robot. As we move that around, we can shrink or increase this manipulability. So as I pull this up here, remember there's that singular position that's right here, and now we've hit that singular position. So the volume of this has gone down to 0 because now instead of 3-dimensional, it's planar. As soon as I move this out of that set, then I'll be able to get, you can see that now we've got some volume to that. So this is this ballerina pose. Right there. We can do worse than that. If I had this one directly upwards and this one as well, now it goes into a 1-dimensional set. You can see there's no movement at all there. So my manipulability measure goes down to 0. But as soon as we pop that out of there, then we're okay. You can also get into that singular set if we had this one off to the side here, and then have this one locked in the elbow out position. See that now we've got this singular set here, where it's almost flat here. There's no volume to that. Here is a two-link robot. We've seen these before. I'm showing both manipulability ellipses, both my linear velocity and angular velocity. The angular is not exciting, but over here you can see as soon as I split off here, then we get a two-dimensional set. Here is a robot that's got a prismatic joint out here. So as soon as we move that prismatic joint out, then we've got a two-dimensional set that we can move in. But if that comes down to 0, then it's got no, it cannot move in x and y. And the angular one here isn't interesting. With two links, you don't have both of those. Here's a slightly different robot. Again, it's in a singular position here until I move my D joint outwards. And now I've got a two-dimensional set that it can move in. It can move in x and y, no matter what my theta 1 is, as long as I've got some sort of moment arm. Here's my three-link planar robot, the example that we had earlier in this class. It can never achieve arbitrary rotations. Right here it's in the single position. Everybody is lined up. As soon as I move one of these joints out of there, then we're good. Move back into that singular position, and I can pop that out by moving this. You can't control the singular positions by moving your first joint. So anywhere I rotate this theta 1, I'm still in this singular configuration. You can see my manipulability measure is 0 here until I pull that out. This omega is always in a 0 there. So we need a bigger robot. Here's that example that we had at the beginning. It's in its singular position. As soon as I move one of these configurations out, now it's a 2D set. Then we can talk about optimizing things by moving it around. But there, that is our planar manipulator with 7 rotational joints. Here is a more interesting robot. There's a lot going on here, so I'm going to turn off this manipulability ellipse, and you can see that in this configuration it can move in any direction. So with 9 degrees of freedom, it's fine. However, it cannot move in arbitrary rotations. All these joints are aligned too well to allow that to happen. If I move one of these joints out, then now I've got 3 degrees of freedom in there, and so then I have, I'm not in a singular position anymore. Imagine if I play around with it, though I can find a singular position in my velocity. So let me try to do that. Yep. Can't do it. And there's no way to put this robot into a singular configuration for its velocity. And that's because it's got 2 prismatic joints that are orthogonal to a previous rotational joint, and so it can always move a velocity arbitrarily. Here's a robot that does have singular positions, and so if you look at this, you say, oh, I've seen this robot before. This is that Puma arm with a spherical wrist, and here it's in its singular velocity. We can see, let's just look at one at a time. So here's our angular velocity, singular position. We can rotate that out of here by getting it out of its kinematic singularity with a wrist. So I rotate there, and now we're good with that. Let's go ahead and look at our velocity kinematics. Again, it's in a single position, not in a singular position until we go back to here, because it can easily rotate left or right across here, but it can't do a motion in this direction. So all we'd have to do is rotate this joint a little bit, and then we're out of it. So we're out of this singular configuration for velocity, but we're still in one for the angular velocity. I lied. So now you're here in one that is in for the angular velocity, but and also for the linear velocity. So here, linear velocity is fine, but the angular velocity is in a singular position here. You can see we can easily escape this just by rotating one of our degrees of freedom a little bit. There we go. We're out of that singular position.